What we're going to quickly discuss here is the area of rectangles, and this is the basis of all the area formulas that we use for every other figure. Every other figure, we can bring it back to the area of a rectangle, and you'll see that as the lessons go on. So first we review the area of a square is the square of the length of a side, so just x times x, and that tells you how much room is here. If two figures are congruent, then they have the same area. Notice that the converse of this statement wouldn't be true. Just because they have the same area doesn't mean they're congruent. But if you're told up front they're congruent, then they do have the same area. The area addition postulate joins our other addition postulates, basically saying that if you add the sum of two small regions, you get the area of the larger region that they make up. The area of a rectangle is the base times the height. And again, the base can be any side, and the height is also the altitude or the perpendicular to the line containing the base. And the area of a rectangle equals the product of its base and height. Basically, it's measuring how many different squares, 1 inch by 1 inch or 1 centimeter by 1 inch centimeter squares, can fit into the particular rectangle. So the area of the base times the height is coming from telling you how many squares long it is. So for example, this one is 6 squares long and 4 squares high. Well, you could count them, or you know that 6 times 4, 6 rows of 4, make 24. So that basically comes from the idea of it's this many squares long, this many squares tall, and by just multiplying those, I can figure out how many total there are. So this is a section of true and false. I'd like you to put down true and false to answer these, true and false, and then come back and push play for the answers. All right, for the first one, this is false. You could actually have a rectangle with, say, an area of 24 and a triangle have an area of 24. A rectangle and a triangle aren't congruent, so this would be false. If two figures have the same perimeter, then they must have the same area. This is also false. There's a lot of different examples there. You could draw two different rectangles that have the same area, or perimeter, excuse me, but have different areas. If two figures are congruent, then they must have the same area. This is true, and we said this on the previous slide, I guess the first slide, right here. If two figures are congruent, they have the same area. Every square is a rectangle. This is true. Every square does have 4 right angles. Is every rectangle a square? This is false, because not every rectangle has 4 congruent sides. And the last one, the base of a rectangle could be any side of the rectangle. That is true. You can use any side. Now what you're going to do is you have a table here. B is base, H is height, capital A is area. Same here, base, height, area, and little p is perimeter. So using this information, I would like you to fill in the table. So please push pause and work through this table. All right. On the next slide, you see the answers. I multiplied 12 times 3. I did 54 divided by 9 to get 6. 4 times 5 is 20. Root 3 times root 3 is 60. I think you get the idea here of what you needed to do to get your answers. But if you do have any questions, please, you can email me and ask me the question, or see me in class and ask the question if you're not exactly sure where a number came from. But I feel pretty confident that you knew how to do these. Okay, the next slide is the same idea, just has a little more algebra to it with the variables. This should be k squared. That's what that's trying to say, k squared. So again, work through these. You might need that little part is 6. If you have the printout of the notes, you'll see it. And so again, I'd like you to push pause, work through these problems, and then come back to check your answers. Okay, I have the answers here. Here I had to distribute the 4y through. And then for the perimeter, I had to double this, and that got me the perimeter. Over here, I had to take 2x minus 1's away. So that's 2x minus 2, and then figure out what was left and divide that by 2. Okay, and then I multiplied these two together to get the area. Over here, again, this was k squared, so if you factor out the greatest common factor of k, that's where this came from, and you're left with k minus 4. In the final example, It was a weird shape, but we're going to use that area addition postulate. I broke it into 2 rectangles, and there is more than one way to divide this shape up. As long as you get 36, you're in good shape. This is just one example. I drew a line here, which left me a 6 by 5 rectangle. That's an area of 30. This has a width of 2, because the whole thing was 8. I cut off 6, that's 2. This had a whole length of 5. I cut off 2, so that was 3. 2 times 3 is 6, and add those together, you get a total area of 36. So area of a rectangle, we're going to take everything back to that as we move through other shapes, but that's the basis of 11.1.